All right, well, happy Monday. Thanks for being here. And today our topic is random number generation. So a lot of Monte Carlo classes start with this topic. This is kind of like the first topic in Monte Carlo methods. I like wait till the third week to bring it up. That's just because I like to try to fit things into some context. And so I started off with kind of, Bayesian ideas, and then we talked about Monte Carlo integration and estimating integrals, with a Monte Carlo method. And this is kind of where we left off, right? So last week we talked about Monte Carlo integration. We can estimate, the mean of some kind of function, when you apply it to a random variable. And then we can use that to estimate the quantities of integrals, which is helpful because, especially in Bayesian statistics, the quantities that you want are often the results of some kind of integral. Okay, so you often have some kind of random variable, you have some kind of function. To get the quantity you want, you got to do some kind of integral, and sometimes those integrals are hard. And that's where Monte Carlo methods make it easier to get at least a ballpark estimate. And if you let it run longer, then you'll get a more precise estimate of that quantity. Okay, so everything is, we're just looking for an estimate. And so far, we said this quantity represents the expected value when we apply the function h to the random variable x. And x is a random variable, and the PDF of x is this function f. And so far, all of our functions have been probability distributions that are well understood, that have built in. Our computer, R, has these functions that generate quantities from these random variables, right? So we have generate something from the uniform distribution, generate something from the normal distribution, generate something from the beta distribution, or generate something from the gamma distribution, exponential. These are all kind of probability distributions that you learned about in 100B. There are probability distributions that have been implemented into the computer. So we've been able to generate all of these values from known distributions. It's really easy, right? You just say R exponential 1 million, or R beta. I want 1 million values. Okay, so that's been easy. And then last week we talked about importance sampling, and we said, what if you can't generate values from a particular distribution? Can we account for that somehow? And we said, well, if you know the PDFs of all of your distributions, then you can generate from one, and then you weight it, and then that will fix the problem. And then, but today what we'll look at is, okay, if you can't, if here's some PDF that, we don't know how to generate values from, can we still try to generate values from that? And that's what we'll look at today. Okay, so today we'll start introducing this idea of generating values from just kind of any distribution. As long as you have the density function, can we generate values from that? Okay, and so we're going to start with the inverse CDF, inverse cumulative distribution function, and then our next lecture on Wednesday we'll look at rejection sampling, and those are kind of like two major ways for generating random values. All of the things that we're going to look at today, we start off with this basic premise that we can generate random uniform numbers in the first place. Okay, so it says, I wrote, nearly all future algorithms for random variable generation depend on the ability to generate random values from a uniform distribution. So we will we will start off with this assumption that we have somewhere in our computer, we have a function where we can do R, like in R, we have RUnif, right? RUnif to generate uniform random values. And then, if you go on Python, you do like random and stuff like that. And we're going to just assume our computer can generate random values. Now, if you took a Monte Carlo class, this used to be like, you would spend like a couple weeks on just this topic of generating random uniform numbers. And it wasn't like this trivial thing. And it was tough. And in fact, if you didn't have access to a computer that generated random uniform values, like in the early days of computing, what you would have to do is you'd have to buy a book of random numbers, okay? Did any of your introductory stats books have like a table of random numbers? In like the back in the appendix, like next to the normal table, there was also a table of random numbers or something. Some of your intro stats books might have that. And yeah, I think you can still buy, like just for like kicks. Here's this book, 1,000,000 Random Digits. Let me see can we look at the inside? Oh, we can't look at the inside. Price increase. Okay. Do they have any images? Okay. It used to be you would just buy a book, and inside the book there would be a bunch of random digits. Okay. But yeah, we don't do this. I put this silly slide in here. So when we ask the computer for random numbers, they're not random, right? They are what we call pseudo-random, in that they look like they're random, they act like they're random, but they're also not random, because I could do set seed and you can do set seed, and then I produce the exact same numbers you would produce, right? So that means it's not random. Versus like if I flip a coin 100 times and you flip a coin 100 times, like there's no way we would get the exact same outcomes, right? But then at the same time, there's a question is like, is the coin flip actually random? Because if you think about it, it's just like the result of physics. And if like we could measure exactly how strong my thumb is flicking up, and I don't know, all of these other physical properties of like air resistance and how bouncy the surface is and the weight in the coin and stuff like that, like maybe it's not actually random, right? And then there's this question is like, is anything in life actually random? And I actually don't know. And there's like, like as far as like, as people, do we have free will versus like, are the words that I'm saying just the result of like the electrical signals happening in my brain, which are really just the results of physics? And if you think about it too hard, it's like, well, I don't think we can actually know the answers to these things, right? And there's different, like you can look up determinism versus libertarianism. Libertarianism in this regard is regarding free will, and these are kind of like the philosophy. Anybody take a philosophy class and discuss free will? Okay, well, it's just people discussing stuff that we can't actually know, right? But there's logical things that come out of it. But anyway, we'll talk about these pseudo-random numbers, and our computer is able to generate random numbers using R uniform. They're not actually random. They just kind of look like they're random. We have a bunch of tests, like stress tests, that kind of say like, if they're supposed to be random, do we have if they're supposed to be random uniform and I generate a whole bunch of values, do they look like the uniform distribution? Does the number 5 appear just as often as the number 6 or something like that? So we have, these different kinds of tests that we can run. And one of the kind of classic methods for generating random numbers was what we called the linear congruential generator. And this was an old and well-known way for generating pseudo-random numbers. And the way it worked was you start off at some arbitrary number, you multiply it by some constant a, and then you add another constant c, and then whatever that result is, you do modulo another value m, and then you take whatever value that produces, and this often would produce some kind of number that could exhibit random properties. Okay, I'm going to give you a set that's going to give really bad random properties. So I could start off with the initial value 1. We're going to use constants 2, 0, and 9. Okay, so my first value will be 2 times 1 plus 0, and then I'm going to mod 9. So I get 2 mod 9, and that's going to be 2, right? So if I do, and then I plug in 2, and 2 times 2 is 4, and 4 mod 9 is 4, and then I multiply that by 2, and 2 times 4 is 8, 8 mod 9 is 8, and then I multiply 8 by 2, and I get 16, 16 mod 9, so 16 divided by 9 is 1 remainder 7, so we're going to get 7, and then I do 2 times 7, I get 14, and then 14 mod 9 is, 1 remainder 5, so I get 5, and then 2 times 5 is 10, 10 mod 9 is 1, so we're looking at the sequence and we get 2, 4, 8, 7, 5, 1, but then I do 2 times 1 and I get 2 mod 9, and then we're going to end up at 2. And so here the cycle is going to repeat. So the random number it generates will be 2, 4, 8, 7, 5, 1, 2, 4, 8, 7, 5, 1. So this is not a good thing, but and we can see this is going to be the number sequence that it generates: 2, 4, 8, 7, 5, 1, 2, 4, 8, 7, 5, 1, and we can see this is just a way to generate this: a times x plus c mod m, and then whatever it outputs will be our output, and we can say generate a bunch of these things. But despite this being a terrible example, using these constants, 2, 0, and 9, if you had different numbers, okay, it could actually generate something that looks quite a bit like a random number here, okay? And so if you use this value for A, this value for C, and this value for M, it's going to generate a whole bunch of numbers, and these numbers will act kind of pseudo-random. And you can look up on Wikipedia the linear congruential generator, and it will show you some of the values for A, C, and M that were used for different kind of different computing languages. So early days of the C computing language, this is how it generated random numbers. And so, we could kind of look at the properties of this. And so if I take the numbers it generates and I divide everything by 2 to the 31, then that's going to scale all the values between 0 and 1. And, it's not perfectly uniform, but kind of. Here I can look at the empirical CDF, and we can see, in black versus red, it looks fairly good, but, not perfect, okay? And that was that, okay? Today, when you use R uniform on your computer, almost all the numbers, almost always it's using this algorithm called the Mersenne Twister. So this linear congruential generator, it's pretty easy for us to understand, and I can explain it. But now the random number generator that we often use is the Mersenne Twister. It uses a Mersenne prime, I guess 2 to the 19,937, whatever that number is, minus 1. And I guess a Mersenne prime is a prime number that is 1 less than a power of 2. And it was developed in 1997, So now it's pretty old. What's that? 25 years old now. 26 years old. And it's kind of the default number generator in R, also Python, also MATLAB, versions of C++, so on and so forth. The algorithm itself is really, really, really complicated. It uses like bit shifting. So, you think about your 2-digit binary number, and you can bit shift, which will basically, multiply either by a power of 2 or divide by a power of 2, and it kind of basically takes your, 101 will get shifted, maybe to the left to be, 1010 or, whatever it is. And yeah, so anyway, it's complex. I tried to read the paper to try to understand it, but it got a little bit too into like, kind of like assembly stuff for like computer programming. So it was like, oh gosh, I don't quite understand this. So anyway, all to say, it's very popular. It's passed a whole bunch of different statistical tests as far as like, does this act like a random number? And it acts like it's random. That said, it's not cryptographically secure. So if you have to do something for like encryption, where you don't want somebody to hack and figure out what numbers you're using, you don't want to use the Mersenne Twister, because I guess once you see a sequence of like, say, 10 random numbers generated by the Mersenne Twister, you can kind of backwards solve and figure out what its starting seed was, and then you could start predicting the next set of numbers. Okay, so in that way, it's not cryptographically secure. But as far as like what numbers is it generating, they act like random numbers for our things. Okay, and so that's what we have. All right, so we're gonna just get that out of the way and just say we're gonna treat this generation of random uniform numbers as if it were a solved problem, and we're not gonna worry about it. Okay, it's kind of like, does anyone know how your calculator takes the square root? Like if you type in square root of 2, or does anyone even know how to take a square root by hand? Not really, right? But we don't worry about it, okay? We understand this concept of taking a square root, but do we have to actually know how to take a square root by hand? I don't think so, right? It used to be something they would teach you in class, in like school. You would learn how to take a square root by hand, and there's a way to do it. I don't know how to do it, okay? We say like, all right, you can multiply and you can do long division, and we say if you can do long division, you're good enough, and then that's good. Okay, we don't bother trying to teach you how to take square roots by hand. We just say, hey, the computer can do it, and that's good enough. And we understand the concept of a square root, and we say, hey, that's good enough for me. And so now generating random numbers, it used to be like, okay, can we figure out how to generate random numbers ourselves? I've kind of shown you this linear congruential generator, which is good enough. I'm not going to bother trying to teach you how this Mersenne Twister goes, but we're going to just kind of stick with it and just say, hey, the computer is able to generate random uniform numbers, and that's good enough for me. And I hope you'll buy that. Okay, let me give you your first view quiz answer. It is week 3 Monday, or your first answer is the letter C. C as in cat is our first view quiz answer. C. C as in cat. Okay, so yes, question. You can't access? What did I do? Available from 9 a.m. That's the problem. Okay. Okay, it should be working now. Okay. All right, so the rest, we will focus on generating values from different distributions. We're going to rely on this assumption that we are able to generate values from a random uniform distribution from 0 to 1. So we're going to just assume the computer is able to give us random uniform values. And therefore, the PDF of the random uniform it has a PDF of 1 for values between 0 and 1, and then it's 0 everywhere else, and we just use RUnif to generate values. And the first way we are going to use generate random values is if we can generate values from the random uniform, we can then use the inverse CDF to generate values from a probability distribution. So if we have the CDF, cumulative distribution function, we can invert it, and then the inverted CDF, okay, the inverse CDF can be used to generate values from that particular random variable. So if we think about what is the definition of the CDF, okay, it is the CDF, which we write capital F of some location little x, is the probability that the random variable x is less than or equal to that value little x, right? So if we talk about the normal distribution, the CDF of x equals 0 is 0.5, right? Because if we think about the normal distribution, half of the values are less than 0. So what is the probability that a random variable from the standard normal is less than 0? That's equal to 0.5. And that's basically equal to the integral from negative infinity up to that location x. In our case, we're saying the normal distribution, we're going to go to 0 of the PDF, the normal PDF, right? And then, so for the normal distribution, if we plug in x equal to 1.96, then the CDF of 1.96 for the normal will be 0.975. There's a 97.5% probability that your normal a random normal variable will be less than 1.96 or something, right? And so the CDF takes the entire support of x. So for the normal distribution, it goes from negative infinity to positive infinity, and it maps every value on the support to a value between 0 and 1. So that's what the CDF does, right? Because the lowest value of the CDF can be a 0, largest value of CDF can be is 1. And any kind of distribution is going to go, the CDF has a range of 0 to 1. Okay, this thing, the probability integral transform, says that if you have any kind of continuous random variable x, and that random variable has the CDF, big F of x, okay, then if you define a random variable, and we'll call this u, which is going to be equal to f applied to a random value of x, okay, that distribution of u has a standard uniform distribution. So if I say generate a random number and I plug it into the CDF, that CDF will be a value between 0 and 1. And if x is a random variable and it has the CDF f and you plug it in there, then that resulting value between 0 and 1 will have a uniform distribution. So, which it feels a little bit strange to state it, but also it's a little bit kind of like maybe like so obvious that it feels strange when you think about it, right? So if I just if I generate random normal values, and then I plug all of those values into the CDF. So, I ask, what's the cumulative distribution function for these random normal values? Then that's going to convert all of those normal values going anywhere from negative infinity to positive infinity into values between 0 and 1. And then if you look at the distribution of values between 0 and 1, it will look like a uniform distribution. Okay? So if you say, hey, give me R norm values, random normal values, and then you plug them into P norm, which takes those normal values and turns them into, cumulative probabilities. All of those values in P norm, when you can look at them, they're going to have a uniform distribution. So, so this function big F of x transforms x into basically a random uniform value. Okay. And this is the principle of the inverse CDF, is that, okay, can I reverse it? And the answer is yes, okay? If I start with a random uniform value between 0 and 1, I can use the inverse of CDF, and that will transform it to a random variable of big X, okay? So this is the definition of the inverse transform method, or the inverse CDF method. So we're going to say we have some random variable X. All right, this is a continuous random variable with cumulative distribution function big F of X. The inverse is if you take the inverse of F and apply it to a random uniform value, which we're going to define as the smallest value of t such that big F of t is greater than or equal to u, then this distribution is going to have the distribution of random variable X. This is a lot of math here, okay? So this is, what is the smallest value of t that satisfies this quantity, that the CDF applied to t is greater than or equal to u, where u is a random value between 0 and 1. And that result, where you plug it into this function, is going to have distribution X. Here's kind of the proof. And this is just, we're going to say, all right, the uniform comes from here, and we're going to just say, all right, what is the probability that the inverse CDF applied to u is less than or equal to X? Okay, well, we can apply F to the inverse of this, and that, F applied to the inverse of F is going to cancel it out, and we're going to get u, and this is going to equal, if we apply F to both sides of this inequality, then we will get X over here, big F of X. And then, so what's the probability that u is less than or equal to big F of X? Well, that's just going to be F of X, right? Because the probability that a random uniform value is less than any quantity P is going to equal P, right? So the probability that u is less than or equal to big F of X is just going to be big F of X, and therefore the probability that inverse F of u, okay, inverse CDF of u being less than or equal to X is F of X, and so that's just to say that inverse CDF of u has the same distribution as F of X here. So u has this thing has the same distribution as X. Okay, so this is the summary page. Let's just try out some examples. I think it will make it's a little bit easier for us to kind of grapple with this if we try out some example. All right, so here's kind of the simplest thing. Let's say you are able to generate values from 0 to 1, right? So we're saying we can generate values from 0 to 1. And let's say I give you a challenge and I say, I want you to then generate random uniform values between 10 and 20. I think that's the example I want to do, yeah. So how could you go from 0 to 1 to values between 10 and 20? What would you do? And I think you could do this without even learning inverse CDF, because I think this is the most intuitive part. So we're going to generate values between 0 and 1, and let's say you generate the value 0.5. And if you say, well, we want it to kind of correspond to values between 10 and 20, 0.5 should correspond to what value? Like 15, right? Halfway between 10 and 20, all right? And then you could say, okay, well, 0 would then correspond to 10, and then if we generated 1, that would correspond to generating the value 20. And okay, so what is the kind of the rule there? You would say, all right, well, let's just take the value between 0 and 1, we'll multiply it by 10, and then so that will kind of scale it to be wider, and then we'll just shift the whole thing 10 points up, right? And that's exactly what we end up doing when we do inverse CDF. But here we'll formally show why our intuitive thing lines up here. Okay, so the PDF of a uniform variable going from A to B is 1 over B minus A. So if we're going from 10 to 20, we're going to say, okay, well, that's going to have a span of 10. So our PDF is 1/10. 1/10 for all values between 10 and 20. And then it's 0 everywhere else. And then the CDF is going to be the integral starting at A up to whatever location X is of our PDF dt, right? And so we're going to plug in X into this, we get X over B minus A. We plug in A as our starting location, we get X minus A over B minus A. So this is our CDF of this random uniform, X minus A divided by B minus A. So if we say, hey, what's the CDF of 15 on this value from 10 to 20? We do 15 minus 10, we're at 5, we divide by 10, and the CDF of 15 is 0.5. We plug in 20, we get 1. If we plug in 10, we get 0. So that's exactly what we have. Okay, so now we're going to say, we're going to start off and we're going to solve for the inverse. So we're going to say f of x is equal to u, and we're going to kind of try to get this in terms of x, and we're going to just rearrange things. So our CDF is x minus a divided by b minus a times u. We're going to multiply both sides by b minus a. And we're going to get x minus a is equal to b minus a times u. And then we add a to both sides. So this is exactly what we get. So when we say, hey, I want to generate random values between 10 and 20, we're basically taking our random uniform value, multiplying it by that width, 20 minus 10, we're multiplying it by a width of 10, and then we're shifting or sliding the whole thing up 10 units. So the inverse CDF is we take our uniform value, multiply it by b minus a, then we add a. So again, if we plug in u equals 0, then we would get 10. If we plug in u equal to 1, we will get 20. If we plug in u equal to 0.22, if we generate a uniform random value, then we would get 12.2. If we generate a random uniform of 0.5 and we plug that in, we get 15. And so this would be inverse CDF of, for this random uniform thing. Okay, let's try for a different, all right, is that okay? Random uniform, inverse CDF. All right, let's try for an exponential. So an exponential distribution this is the PDF, right? So as x goes on, our PDF, I don't know if I can even have this, right? And then what is the CDF? Looks like that, okay? And then, so this would be the CDF. This starts off at 0 and asymptotically approaches 1. And then what would the inverse CDF be? Okay, so you're basically, what do you call it? Mirroring it around this, right? I'm like really nervous that I'm messing this up here. Okay. So the PDF of a random exponential has this thing, the CDF. So we're going to integrate. So exponentials are only positive values. So I guess technically we integrate from negative infinity up to x, but it doesn't exist for anything less than 0. So the integral from negative infinity up to 0 is just 0. And then so starting at 0, then we actually have values. So we're going to integrate from 0 to x of lambda e to the negative lambda t. And we're going to get 1 minus e to the negative lambda x. Okay? Because, you plug in 0, the integral of this, and you get, that evaluates to that. Okay? I think negative 1. And then, so this is what we have here. And then we're going to solve for x here. Okay, so we set this equal. We say the CDF is equal to u, and we're going to get 1 minus e to the negative lambda x. We're going to set that equal to u. I'm going to subtract 1 from both sides, and then I'm going to multiply by negative 1. I'm going to get e to the negative lambda x is equal to 1 minus u. And then I'll take the log of both sides. Log, always natural log here. And then I'll divide both sides by negative lambda. Okay, so I get negative 1 over lambda log 1 minus u. And so I can plug in a uniform value. Now, 1 minus u has the same distribution as u itself. So a lot of times when we talk about generating values, we'll just plug in u rather than 1 minus u. I mean, the direct transform is 1 minus u, but then if you think about, okay, what's a random, if you have a random uniform value that generates values between 0 and 1, 1 minus u itself is also going to be a random uniform value between 0 and 1. And so, so this will be our inverse CDF here. Okay, negative 1 over lambda log of u. So yeah, u being a random uniform value, okay, between 0 and 1, log of the random uniform value is always, and log of a value less than 1 is always negative, and then you do multiply by negative 1 over lambda. So let's say we just want to generate values from the exponential distribution. So in this case, 1 minus u, this would actually reverse from, so here's 0 to 1, but here, because I've flipped it to 1 minus 0, we're going to get just the opposite of this. But anyway, so we'll get, so if we plug in u into negative log of u, okay, if we plug in 0, this will produce infinity. And then if we plug in 1, we will produce 0. And then what kind of values do we get? Plugging in, say, 0.1 will generate 2.3. So going from 0 to 0.1 brings us all the way from infinity down to 2.3, okay? But then the gap from 0.1 to 0.5 brings us from 2.3 to 0.69. And then going from 0.5 to 0.9 will bring us from 0.69 to 0.105, right? So we can see that values closer to 0 show up a lot more frequently, and values farther from 0 show up with less frequency, right? Because I guess I could space more of these out, but we will, we can see that it's a lot easier to generate values, say, closer to, say, between 0.1 and, there's equal probability going from 0.1 to 0.5 as 0.5 to 0.9, right? So this is a span of 0.4, and this is also a span of 0.4. So that span of 0.4 covers kind of a range of values going from 0.1 to 0.7. And then here, that equivalent generates 40% of your values come from 0.7 to 2.3. So that's a much bigger range. And so if we were to generate a whole bunch of these values, this is kind of what it looks like. So I said, generate a bunch of random uniform values, and then apply negative log of u, okay? And when you apply negative log of u, it transforms them as such. And then I can say, all right, let's make a histogram of all of those transformed values. And this is what the histogram of all of the transformed values look like. And we can see, oh yeah, a lot of our values, most of our values are less than 2. And then, we don't have very many values between 2 and 4. And we have very few values greater than 4, okay? But it's still possible to get a value as 8. And it's still possible to get, if you have a value very, very, very close to 0, you can get a really big number, right? Theoretically, we can get as big as infinity. All right, so this is the histogram, and then I can plot the theoretic density, which is our exponential function, exponential PDF there. I can also plot, how does the CDF compare to the empirical CDF, right? So here I'm just plotting, here is my actual values of X, and I'm going to say, give me the empirical CDF, okay? So I can plot the empirical CDF of X, and then the theoretic CDF is using the P function, right? So in R, the theoretic CDFs are always, P whatever, P exponential, P norm, P whatever it is. So in our case, we just want the theoretic CDF. As we can see, there's very close alignment between our empirical CDF in black and the theoretic CDF in red. We can conduct a statistical test to see if there is deviation between the empirical CDF and the theoretic CDF. That is I don't know if you've heard of this, the Kolmogorov-Smirnov test. So this is a statistical test that we can use to see if two sets of values, two samples could come from the same distribution. It could also be used to test if one set of values is coming from a theoretic distribution. So this is what we're going to do. We're going to take our actual values, our random values X, compare it to the theoretic distribution given by P exponential with rate parameter equal to 1. And here it says, okay, this is the one sample Kolmogorov-Smirnov test. And in our case, what we want to see is we want to find no evidence against the null hypothesis. The null hypothesis is that our data comes from this theoretic distribution, and when we run it, we get a p-value of 0.3886. And so to us, that means we do not have enough evidence to reject the null hypothesis. So it just says, this sample of 10,000 values, we don't have evidence that it's not coming from the exponential distribution, okay? And again, just the way hypothesis testing works in statistics, this doesn't prove that it's coming from the exponential distribution, but we can't do that in statistics. So all we can say is, hey, I've got 10,000 values, and right now I don't have any evidence that they're not coming from this exponential distribution. So I don't know if you're satisfied, but I'm satisfied that this looks like the exponential distribution, right? Visually it looks like it, the CDF looks like it, the Kolmogorov-Smirnov test says it kind of looks like it too. All right, let me give you your second view quiz answer. Is the letter D. D as in dog. D is our second view quiz answer. This inverse CDF method is actually how R generates values from the normal distribution. So there's a little bit of irony here, because in 100B, we always tell you that there's no closed form solution to the CDF of a normal distribution, right? You say, here's your PDF of the normal, but if you try to integrate it from negative infinity to X or whatever, we don't have a closed form solution. So in that regard, we don't have a functional form of the inverse CDF of the normal distribution, right? So we don't have a closed form solution for the CDF. We also don't have a closed form solution for the inverse CDF. However, our computers have there's a functional approximation to the CDF, okay? And I don't know the details of it, but there's an approximation that our computers can use. I think it's like it's like a bunch of polynomials just added together for a quick calculation or something. And it's a good approximation. It's accurate up to 16 decimal places. And that's like the limit of floating point accuracy anyway on the computer. So even though we don't have a closed form solution analytically, we have a numeric approximation that is accurate to 16 decimal places, which is basically as accurate as our computer is capable of doing anyway. So we have this function, right? So we have p norm, which is an approximation, and then q norm is the inverse of that. And when you ask the computer to generate random uniform values from the random normal values, random values from the normal distribution, it actually uses that approximation q norm. It uses the inverse CDF. You can try this out. So if you ask R to generate R norm, and you set a seed, and then you say, hey, generate random uniform values, you can get back the same R norm values by plugging in your random uniform values into Q norm. So for whatever reason, it does every other value, but let me just kind of show you. So here, if I do set seed 1, and I say, hey, give me 5 random uniform values, these are the values it produces. 0.2655, 0.372, we skipped that one. So, we plug in 0.2655, 0.57285, 0.20168, okay? And so if I take this number, 0.2655, and I plug that into the inverse CDF of the normal distribution, it says, hey, that's negative 0.626. And then if I take this value, 0.5728, and I plug that into Q norm, okay, then it gives me 0.18364. And then if I plug in 0.20168, it gives me negative 0.8356. Okay, and let me just go back, and if I say set seed 1, and I say, hey, give me 3 random normal values, we get those exact same values. Negative 0.626 right here. This value and this value is exactly the same. And then, what happened to my screen here? This next value, 0.1836, is 0.1836, negative 0.8356, and negative 0.8356. So it's just kind of interesting that in our computer's generating random uniform values and then plugging it into the inverse CDF, okay? Or at least the approximation of the inverse CDF are good enough approximation here. So we have that, okay? Which is pretty neat. Okay, so here's another example. Let's say we wanted to generate values so that the PDF looks like this. Okay, so we have a piecewise function for the PDF. I guess a triangular distribution, and this is technically this would be the distribution of a sum of 2 random uniform values, right? So if you take in if you generate a random value between 0 and 1, and you take a random value from between 0 and 1, and then you add those two together, you would get this distribution. You would get this triangular distribution. It's similar to like if you take 2 dice and you roll 2 dice, you have 11 possible values. You can get as small as 2 and as high as 12, and 7 would be the most common. And if you plot out the distribution that's discrete, you also get a triangular distribution. And if you just kind of extend it up to a uniform, basically you get this distribution. And so the PDF looks like this. It is the PDF is x for values between 0 and 1, and then it's 2 minus x for values between 1 and 2, and it's 0 otherwise. Okay, so so this is kind of silly because obviously if I said, hey, here's a new random variable x, which is just the sum of two random uniforms. The easiest way to just be to generate two random uniform values and then do it. But we're going to do inverse CDF just to kind of prove our point here. It's a little bit of a pain to do it, but we can do it. Okay, so here's our PDF, and then we can see, you know, if we integrate all the way from 0 to 2, I mean, basically it's a triangle, right? Base times height divided by 2. So our base is 2, our height is 1, and we can see that the PDF integrates to 1, or area under the curve is equal to 1. All right, so we have to find the CDF. Our PDF is piecewise. Our CDF is also going to be piecewise. So the CDF is 0 to x t dt, right? Because our PDF is x, so we have to kind of use a placeholder letter. Why is my thing all messed up? Okay, so integrating from 0 to x, you know, we get our antiderivative is t squared over 2. Evaluate from 0 to x, and we just get x squared over 2. All right, straight enough, or simple enough, and that's for values between 0 and 1. Okay, and then the other half of the CDF, we integrate from 0 to x of f of t dt. Okay, and in this case, so our CDF is x for 0 to 1, and then 2 minus x for 1, x is values between 1 and 2. So here we have to integrate from 0 to 1 of t dt, and then we go from 1 to x is 2 minus t dt, okay? Because here this is for all values where x is between 1 and 2. So, so we have to kind of take the first part of the PDF, okay? And so the first part of the PDF is just going to evaluate to 1/2, right? We're basically asking, because we want to get the CDF of this side after 1. So basically, this first part is going to be the area of this half of the triangle, which is just 1/2. But mathematically, we can work it out, and so we get t squared over 2 evaluated from 1 to 0, and that's going to evaluate to 1/2. And then this side, we get 2 minus t dt, and so that will become 2t minus t squared over 2, and we evaluate from 1 to x, and so plugging in x, we get 2x minus x squared over 2. You plug in 1, and you get minus 2 minus 1/2, so this is minus 1.5 over here, so you have 1/2 plus this minus 1.5, and so this becomes negative 1 plus 2x minus x squared over 2. Is that all right? So we just have kind of this piecewise our CDF. So for PDF, it goes like this. Our CDF goes like so we have t squared over, so basically we have half of a parabola up to here, and then this one is like kind of a you know, see, so just imagine like a parabola over here and then a parabola on this side, and you're just kind of like taking this from here to here is kind of how it evaluates too. So this has function basically x squared over 2, and then this is 2x minus x squared minus 1 over here. Maybe I should rewrite it. Minus x squared. All right. Minus x squared plus 2x minus 1. It's kind of our PDF like this. Right? So you have kind of like a parabola over there, and then if you can see that. All right. So that's the CDF. And then now we want to invert this. Okay, so basically we want to take this CDF and we want to get an inverse of this. So we also have to do this piecewise. So for values where x is between 0 and 1, we're gonna set x squared over 2 because we have x squared over, yeah, so the left half, okay, x squared over 2 is equal to x, or so we're gonna set x squared over 2 is equal to u, and then we want to solve for x, so we multiply both sides by 2, and then we take if we have x squared is equal to 2u, solving for x, we get plus or minus the square root of 2u, and you have to actually pause, and you can't just automatically take the positive side or automatically take the negative side. You have to think like, okay, what values can x be in this case? And so in our case, x is a positive number, so we're going to take the positive side. Okay, but in some cases, depending on how it evaluates, you might want to take the negative side. All right, so always kind of just pause for a moment and think like, if x is plus or minus the square root, do I want to keep the positive or negative side? In this case, we keep the positive side. Okay, so we have x is equal to the square root of 2u. Okay, for values of u between 0 and 1/2. Okay, so just kind of solving for what values of u will produce values of x between 0 and 1. The other half requires a little bit of like thinking back to 8th grade algebra or whenever you took algebra and remembering some of these tricks. Or maybe this was algebra 2, I don't remember. So here, this like, I detailed this out in the notes now because I gave a similar problem on an exam once. And then like so many students were angry with me because they couldn't remember their algebra. But so I was like, all right, you have to remember some of your algebra. So you have to do, so we're gonna take our function, -1 plus 2x minus x squared over 2 is equal to u. I'm gonna multiply everything, both sides by positive 2. So I get 2 minus 4x plus x squared, or basically I get x squared minus 4x plus 2 right now, is equal to -2 times u. I'm sorry, I multiply everything by -2, okay? And then, what do? We will complete the square. So, so if I do 2 minus x, okay? Basically, I have to add a 4 to this side to complete the square. I mean, I have to add 2 to this side to complete the square, and I have to add 2 to this side to complete the square, okay? And students couldn't remember to do that. You don't want to, I think students are used to like factoring and setting it equal to 0 and solving, but we're not trying to do that. We're trying to isolate x here. So we complete the square, and then I'm going to take the square root of both sides. I get 2 minus x is equal to plus or minus the square root of -2u plus 2. And again, we think about what values can x be. So x can be a value between 1 and 2. So in our case, we want the positive side, because if I plug in 2, I will get 0. If I plug in 1, I will get 1. So this is entirely positive. But you might be in a situation where x is going to be, x evaluates to a value between say 3 and 4 or something like that. And in that case, the left-hand side will always be negative, 2 minus 3 or 2 minus 4 or something like that. Okay, so anyway, we do this. So we'll take the positive side, keep the positive side, and then so solving for x, I will add x to both sides, and I will subtract off the square root of -2u plus 2. So this ends up being the quantity. I get 2 minus the square root of -2u plus 2, which I can kind of factor around to 2 minus the square root of 2 times 1 minus u, and this will be for values between of u between 1/2 and 1. All right, so that's that over there. And so here I can use our function and I can say, all right, let's generate a bunch of random uniform values. And I will do square root of 2 times u to generate kind of our x values. And then if u is greater than 0.5, we want to use the other function, which will be 2 minus the square root of 2 times 1 minus u. So that's what I have there. So for anything where u is greater than 0.5, replace x with 2 minus the square root of 2 times 1 minus u. And so here's x. Here's the histogram of x. And indeed, that looks like the triangular distribution that we want. So that's good. Okay. And we have that. All right. So I think this is a good example. And I don't know, you might see not this exact example on a future exam, but something kind of like you can definitely expect to see an inverse CDF problem on a future exam. All right, so far everything we've been doing has been continuous distributions. We can also use inverse CDF method for discrete distributions. And this is actually, in my opinion, easier to grapple with, but like when you write it out functionally in terms of math, it just feels awkward and clunky, but it's not that weird. Okay, so let's say we have this probability mass function. We're going to generate the values 1, 2, and 3. Okay, and we generate 1 with probability 0.5. So if this is 0.5, and we will generate 2 with probability 0.4, and then we will generate 3 with probability 0.1. Okay, so that's our probability mass function. Adds up to 1. Okay, and then so what does the CDF look like? So here's our PMF. Our CDF, okay, basically we can go from 0 to 1 to 2 to 3. This will have a maximum value of 1 and then 5. All right, so between 0 and 1, anything less than 1, the CDF is 0. And then at 1, it jumps up to 0.5, right? And then, so we ask, so then what is the value at, say, 1.5? Is it 0.5 or 0.9? So how do we define a CDF here? So it's flat between 0.5 to 2, right? So we'll put a circle here, and then we'll put in a dot, so I'll put a circle here also. To 3, and then at 3, it jumps up the last. So this is what our CDF should look like. Okay, meaning, because if we think about what is the definition of a CDF, it is what is the probability that your random variable x is less than or equal to some location, right? So if we're generating, because we can only generate values of 1, 2, or 3. And then so it feels a little bit strange, right? Probability of generating 1 is 0.5, probability of generating 2 is 0.4, and probability of generating 3 is 0.1. But the CDF is this, the span goes, negative infinity to positive infinity. And we say, all right, what's the cumulative distribution function at 1.5. Okay, this is the probability that a random variable x is less than 1.5. Okay, and so really the only value that can be less than 1.5 is 1, and the probability of getting a 1 is 0.5. Right? What's the probability? What's our CDF at, say, 2.7? Okay, the probability that x is a value less than 2.7, there's only two values that it can be. It can be 1 or 2, and the probability that it's 1 or 2 is 0.9. So the CDF at 2.7 is going to be 0.9. So this is how we would produce our CDF at 0.5, or for x greater than or equal to 1 but less than 2, it's 0.5, and x greater than or equal to 2 but less than 3 is 0.9, and then x greater than or equal to 3 is 1. 100% probability that x is going to be 3 or less. Okay, and this is what it looks like. Okay, so that is the CDF. The inverse CDF looks like this. So keep in mind the definition of our inverse CDF. The inverse is the minimum value of t such that the CDF at t is greater than or equal to this value u. Okay, that the CDF at that location. Okay, so if we plugged in, say, 0.326, it is what is the smallest value of t so that the cumulative CDF, cumulative distribution function, is greater than 0.326. Right? So the smallest value has to be 1. Because if I plug in t equal to 1, then my CDF is going to be 0.5, and 0.5 is greater than 0.326. If I plugged in t equal to, say, 0.7, okay, what is the CDF at 0.7? Well, the CDF at 0.7 is what is the probability that a random variable x is less than 0.7, and there's zero probability that your random variable is ever going to be less than 0.7 because the smallest possible value can be is 1. Okay, so if I plugged in 0.7 here, that's not going to work. So the very smallest value of t such that the CDF of t is going to be greater than 0.326 is t is equal to 1. And then if I say u is equal to 0.786, okay, just some other location, 0.786, which is right here, what is the smallest value of t that t could be such that the CDF of t is greater than 0.786? Well, it has to be at least 2. So if we invert the CDF, this is what it has to be. The inverse of the CDF has to be is going to be 1 for any value between 0 and 0.5. And then if u is between 0.5 and 0.9, then it's going to be 2. And then if u, I guess I can write less than or equal to 1, but for 0.9, u greater than 0.9, then it's going to be 3. So it's going to be less than or equal to there. So let's see. We want to go from 0 to 1.5. So it's going to go 0.5, 0.9, 1, 2, 3. That's your inverse CDF function here. So we could generate values like this. Okay, 0 is less than u, u is between 0.5 and 0.9 is going to give us 2, and then u between 0.9 and 1 will give us 3. And so let me, okay, so this is just generalized to any kind of quantity, but let me just write out some code here, right? So if you have any kind of cumulative or CDF of x for a discrete distribution, you can write out the entire table, and it's just going to be the sum of all of these things here. So let me just write out some code here. So here we're going to just say x can be a value 1, 2, or 3, and then the corresponding probabilities is the mass function is 0.5, 0.4, and 0.1. And so how do we generate values from this thing? I'm going to say let's generate one random uniform value, okay? And then we're going to ask, so we're going to start with position equal to 1, and then if u is greater than the sum of the probabilities up to that position, okay, then we will move to the next position, okay? And then when this is no longer true, then we will output x at this position. So if, let's say the first value of u I generate is 0.3. 0.3 should generate a 1, okay? So if I start off, if my u is 0.3, I start off at my first position. The probabilities, the cumulative probabilities up to that position is 0.5. So 0.3 is not greater than 0.5, so I'm not going to increment my position, and I'm going to just return x in the first position. Let's say I generate a value 0.8. All right, 0.8 should generate a 2. So u is going to be 0.8. I ask, okay, is 0.8 greater than the sum of the probabilities from 1 to 1? So I start off, and yeah, 0.8 is greater than 0.5. So I'm going to increment the position to 2. All right, position goes up to 2. Now I say, what's the sum of the probabilities of the first two? 0.5 and 0.4. Well, 0.8 is less than that, so this is no longer true. It's going to kick out, and it's going to return 2. And then if, let's say I generate 0.95, okay? Well, 0.95 would require all three values for that sum to be greater than that, so then it's going to kick out the third number there. And so I can do this. I can say, all right, give me some random numbers. So if I say set seed 5, the first value it generates, u is 0.2 and it kicks out a 1. The next value it generates is 0.685, it kicks out a 2. The next value it generates is 0.9168 and it kicks out a 3. So this seems to be working. And here, I don't know internally what R is doing, but I think it's doing the same thing that I'm doing, okay? Because here I said, all right, let's generate some random values of x, where x has these probabilities, the probability mass function of 0.5, 0.4, and 0.1. And so I wrote my function, random discrete, which is just this code right here. And then if you use R's sample function and you specify a vector of probabilities, so I say, hey, sample the values 1, 2, and 3 using this probability vector. I want 30 of these values. And I set a seed, it generates the values 2, 2, 3, 1, 2, 1, right? 2, 2, 3, 1, 2, 1. And then if you use my function that I wrote over here, where I say, hey, generate a random uniform value, and then look it up in here, we get the exact same values. So I think R internally is doing the exact same thing that my function is running, because it generates the same values, 2, 2, 3, 1, 2, 1, and so on and so forth. So it's generating a random uniform value, and then it's kind of looking at, okay, how many, at what point is the sum greater than or equal to that uniform value, and then it kicks out the corresponding number. So I don't know. I think it's kind of neat that like the little function that we're writing ourselves replicates what R is doing, and it just gives us a little insight into Like, what is R doing, or what is our computer doing when we ask for random numbers? Okay, and so it feels a little bit like, you know, a lot of this stuff, like our computer is very good at generating pseudo-random numbers, and you know, we're replicating some of this stuff. I think it's good to learn how some of these things are being generated when we ask for random numbers here, because that forms a basis for pretty much all the stuff we do in Monte Carlo study. All right, let me give you your last view quiz answer. Last view quiz answer is the letter A. A as in apple. A as in apple is your last view quiz answer. All right, we will end here for today, and we'll see you on Wednesday.